pretty much quantitative analysis. So this is like your, I guess, calculations. There's a few parts to it. There's like the titration and then the titration calculations that you have, and then also a bit of Ka and Kb, which is like equilibrium, but for acids and bases. Titration is pretty much a quantitative technique that we use to determine the concentration of an unknown solution by using a known solution with a known concentration. And this pretty much has a really long method. It just is using stoichiometry to pretty much figure out the concentration of the unknown solution. So for this, you need to know how standard solutions work. Standard solutions are pretty much solutions that you have an accurately known concentration and you use something called a primary standard. And this is the product that you use before you, do the, volumetric analysis. And a primary standard needs to be very pure. It needs to be stable. So that means not, losing its moisture or even gaining moisture from the air. It should be hydrophobic, which means it does not absorb water within the atmosphere, because that means it'll just be changing mass over time. And it also needs to have a reasonably high molar mass so that, when you're doing calculations and when you're weighing it, it's not going to be as inaccurate. And it should have a known chemical formula. When you're doing a standard solution, firstly, get a proper primary standard. Then calculate the amount of solid that you need. So just weigh it on an electronic balance. Then fully dissolve the solid in a small beaker using distilled water or deionized water, whatever you want to call it. And then transfer that solution into a volumetric flask. You can clean the volumetric flask using water before you put the solution in, just so you're not contaminating anything. And then you just fill the volumetric flask until you get to the calibration line, and make sure you have, once you're reaching the calibration line, you want to do it dropwise so that you're not going overboard. Otherwise, you just have to start again. And then you insert the stopper and then you invert 20 times. Ideally, that's what you want to write in your prac exam or your your trials exam, but you don't have to do it 20 times. That's just too much and it's impractical. And in terms of the calibration line, when you're reaching towards it, it should have the meniscus pretty much like this, so that the bottom of the meniscus touches the calibration line. Hopefully that makes sense. Titration is then a whole nother process. I recommend that you also just watch the videos on YouTube as to how people do it, because explaining it is one thing, but then, looking at on YouTube and, actually seeing it in real life is another thing. So pretty much in titration, each step matters. You need to ensure that you're rinsing all your equipment correctly with the correct liquid. So you'd have equipment like pipettes and burettes, volumetric flask, and conical flasks. Each of them have different rinsing techniques. Your pipette needs to be rinsed with water, and then it needs to be rinsed with the solution that will go into it. So let's say you're using hydrochloric acid and you're pipetting 25 mils of it. Then you need to rinse it with water and then rinse it with hydrochloric acid. For your burette, you do the same thing. So you rinse it with water, and let's say you're putting sodium hydroxide in the burette. Then you rinse it with water, and then you put sodium hydroxide and rinse it. For your volumetric flask, you only need to do water. For conical flask, you only need to do water, and you don't need to dry. Have a think about also what happens if you rinse incorrectly, and if you do figure it out, let me know, or if you have any questions about it, I'm happy to answer. So once you've cleaned all your equipment correctly, you've rinsed it correctly, use your pipette to take up, let's say, 25 mils of hydrochloric acid, if it's a titration between HCl and NaOH, right? So, and let's say we're finding the unknown, we're not finding the unknown, sorry. We're finding the number of moles or concentration of HCl. So once you've pipetted, let's say your HCl, you put that into the conical flask, and then you add a suitable indicator. And now this is really important, because if you've chosen a wrong indicator, your entire, I guess, process is going to be wrong. So in terms of indicators, if it just depends on the salt that's being produced. So let's say for HCl and NaOH, you're producing NaCl. That's a neutral salt. So therefore, you just need to work out which indicator you're going to use. So if it's a neutral salt, you want a indicator that's within the neutral range in its transition period, and the only indicator that suits it would be bromothymol blue. So that's how you choose the indicator. Next thing you do is make sure you fill your burette with the titrant. So let's say that's the NaOH, and then you start doing the titration. How a titration works is pretty much just you open the burette slightly and you start swirling your conical flask. So the liquid from the burette goes into the conical flask, and you keep on swirling it, and then you stop once you see a color change. That's called the rough titration, and that pretty much means that you've gone, like, the first titration will always be you going overboard, and that's why it's called the rough titration. So once you've done that, stop the burette once you see a color change, and note down the difference in volume. So note down the difference between your initial volume and your volume that you've achieved. Next is to do the next 3 sets of titrations. So you pretty much just repeat this very carefully until you've got 3 readings. When you're doing your next titrations, it's really important that you're careful of how much liquid is going from the burette into your conical flask. So what I mean is, pretty much, let's say if it takes 25 mils to see a color change, right? To neutralize the HCl. What you need to do then is, once you're at, let's say, 20 mils, you slightly tilt the stopcock in the burette so that it goes dropwise. So it goes drop by drop, because each drop matters in a titration, because you'll see a color change like this within the matter of 1 mil. So let's say if it's 25 mils you got in your rough titration, you stop your burette and do it dropwise at 20 mils. And once you see a color change, let's say within the final drop, you stop the burette and you record your volume. And that's how you do the titration. And then you perform calculations, which I'll get to later on. Great. This is not working, so let me scroll down. Okay. All right. I'm not that cruel to actually just put a titration question on you, so we'll go through this together. So this is kind of a question that you may be getting in your HSC examinations or your trials. So let's read it together. It's saying that a solution of sodium hydroxide was titrated against a standardized solution of acetic acid, which had a concentration of 0.502. An endpoint was reached. Endpoint is pretty much just the color change that you see. So once you reach endpoint, so once you reach the color change, you just stop the burette. And that means, in this case, we've used 19.3 mils of sodium hydroxide, and we've had 25 mils of acetic acid. So whenever you're doing titration questions, it may seem complicated, but it should be pretty straightforward, because all you're really doing is just using your normal, molar ratio calculations. So let's go through this step by step. First thing you need to do is write down an equation between acetic acid and sodium hydroxide. So let's go ahead and write that down. I don't think I see the equation anyways. So in this case, it's pretty much NaOH plus CH3COOH going to NaCH3COO plus H2O. I know I'm not writing the the states, but you can figure that out. So if we go through it step by step, we can see here that we've got a concentration of acetic acid and we've got volume of acetic acid. if C equals N over V, then N equals CV. So we can calculate the number of moles of acetic acid. So that's pretty much just 0.502 times 0.025, and you'll be getting 0.01255 moles. Ratio, in terms of molar ratio, is just 1:1. So therefore, your number of moles of NaOH is the same. So therefore, you can find concentration of NaOH because you've got volume. So if the molar ratio is the same, number of moles is the same, you just divide it by however many milliliters of NaOH you've used, and we've got 0.1930, 0.01930. So therefore, if you divide number of moles over volume, you should be getting 0.6503 molar. So that's how it pretty much works. I'm just scrolling to see how many questions I've put. I've put a lot of questions, so you can do that in your own spare time, but we are running short of time. So I'll get back to the titration questions later on, because I do want to go through the content with you all. You may be also asked to look at, actually no, you will be asked to look at titration curves. So pretty much titration curves just show how the pH is changing in terms of reacting with acids and bases. So let's just look at each one of them. You can see here that in strong acid, strong base titrations, you have, a decreased pH and then it slowly increases. And that's pretty much the same when you have base being added. And there's also something that you need to know. There's a few important steps in titration curves. There's something called the equivalence point, and that's pretty much the volume of your titrant, so the stuff in your burette, when you've reached a color change. So that's equivalence point. And at equivalence point, you'll be reaching a specific pH, and from that you can kind of tell, which set of acid and base it is. So let's start off with strong acid, strong base. And overall, in terms of pH curves, there's pretty much 5 main points that you need to be able to explore. So you can see here that the first point will be the initial volume. So that is around, depends on the concentration, but in this case it's 1, and that's because it's a strong acid, so therefore it's going to have a low pH. It slowly increases in terms of concentration, and then it shoots up, you can see over here, and then you reach your equivalence point at pH of 7. And that's because you're pretty much just adding more and more base. And then once it has that shoot, it slowly tapers off and decreases in terms of pH rate, like change. And then you end up with a high pH because you have a strong base. In, let's say, a strong acid, weak base, what happens when you have weak acids or bases is that you form something called a buffer. A buffer region is pretty much when you have resistance to pH changes. So a buffer pretty much doesn't want to change its pH. So you can see here that when you have a strong acid and you have a weak base being added, what's actually happening in this region over here when you don't actually have an increase in pH is that you have buffer regions occurring. However, that buffer eventually gets broken and you have a slight increase over here, and then eventually increases in pH. But it's not as high as it would be for a strong base, because remember, weak bases will have a lower pH than strong bases. Next, if we look at weak acid and weak base, you can see here that it has a lower pH in comparison to a strong acid, strong base at equivalence point. And you just explain it similarly. So you can see here that in a weak acid, pH is going to be low. and eventually it would increase due to the addition of base, but you can see here that it's not increasing as much over here, and that's because you have a buffer region. Once that buffer is broken, it keeps on increasing and it shoots up and then eventually stabilizes. And you can see here that it's not increasing as much because you also kind of have a buffer region occurring over here, because you have both a weak acid and a weak base, so therefore there's going to be buffers. And then if you have a weak acid and a strong base, your weak acid is going to have a higher pH than a strong acid. That should also happen here in this thing over here, but I don't know why it's the same as this one. It should be a bit higher, like this. But anyways, if we're just going to explain what a weak acid, strong base thing looks like, you will have a buffer region occurring over here because you have a weak acid, so therefore it will form a buffer. However, buffer is broken, and you can see here that it shoots up because you have a strong base being added, and then it eventually keeps on increasing because of the strong base, and you're producing more hydroxide ions. And this table pretty much just summarizes what the equivalence point looks like when you have different pairs of strong acids and, strong bases, and weak acids and weak bases. So yeah, that is pretty much like a summary of titration curves. I would love to explain it much more in depth, but we are pretty short on time. So I'm just trying to make sure I'm covering the main ideas. I'll just quickly look at Ka, and I think I will wrap it up there. Okay, so in terms of Ka, like I said, it's pretty much just, KeQ, but for an acid. So, if an acid pretty much just ionizes into H plus and A minus, in a simple form, it'll just be H plus and A minus over HA. And if you have a high Ka, you have a strong acid because you have more ions in solution. Low Ka pretty much indicates a weak acid. And you'll see that the weak acids have an awfully small Ka value. And because it's so small, you can't really determine, what's really weak and how weak is it. And that's where your pKa comes in. Because you're using a logarithmic base, you have a smaller scale to work with, so it's easier to determine, what's a strong acid and what's a weak acid. So pKa is pretty much negative log 10 Ka, and it's an inverse logarithmic scale. So if you have a larger pKa, then that means you have a smaller Ka. And you can see over here that if we compare the different Kas and pKas of these acids, you can see here that carbonic acid has the smallest Ka out of all of these three. But it has the largest pKa out of all of these three, and that's because Ka and pKa have an inversely proportional relationship. Not inversely proportional, sorry, inverse relationship. So hopefully that makes sense.